Hello dear student, I am Monir Islam. Today in this video, we are going to discuss an important question of Nbhm PhD 2022. Okay, and this question from functional analysis. Okay, and question ID is 12. So this question from basically functional analysis. Okay, so you have to know previous some knowledge. Okay, so but anyway, if you don't know, you can solve this question. I will give the information that will be needed. Okay, so let's start. Given that gamma be equal to c close interval 1 minus 1 comma 1. Okay, and what is c minus 1? Given that is the normalized space of continuous real root function on the interval minus 1 comma 1 with supreme norm. Okay, means c minus 1 comma minus 1. Okay, I'm the information that given I am writing one by one. Okay, after solving this problem. Okay, it will be easier to solve. So c minus 1 comma minus 1, this will be nothing but set of all function from minus 1 close interval to r, because it says real root function means each value will be each value of the function should be real, and define on the interval minus 1 comma 1. Okay, on the interval, so it domain will be minus 1 comma 1 close interval, and those functions are continuous. Space of all continuous function, which f is continuous. Okay, f is continuous. This is c minus 1 comma minus 1, and this is c minus 1 comma minus 1, and from here you can construct gamma. From here gamma is constructed. Gamma is nothing but c minus 1 comma minus 1 with norm, with subnorm. Norm is subnorm. What is subnorm? For any f belongs to c minus 1 comma minus 1, we have norm f equal to supreme of mod fx for x belongs to minus 1 comma minus 1 for any f belongs to c minus 1 comma minus 1, means f is a continuous function from minus close interval minus 1 comma, f is a continuous function on close interval minus 1 comma 1. Okay, this interval f is continuous, so this is the norm. Okay, and we all know this c minus 1 comma minus 1 under supreme norm, this is a, we all know this is a Banach space. Okay, this is a Banach space. Banach space. Banach space means complete non-linear space. Complete non-linear. Complete non-linear space. This is a complete non-linear space with supreme norm. Okay. Now, one more question is given. Another question: K is with the kernel of the linear functional. One linear functional given. I is mapping as a linear functional. Okay, that map f to minus 1 to 1 f s dx. Okay, on gamma. So what it says? It says there is a mapping I that map f send f to minus 1 to minus 1 f s dx. Okay, you can say I is a mapping that from this from c minus 1 1 close interval. Okay, because f belongs to c minus 1 minus 1, so I is mapping from c minus 1 close interval to real. Because I is functional, so it should map from v to scalar field k. Here k is r. Okay, k will be r or c, so here k is r, real field function. So I is a linear function from c minus 1 minus 1 to r. Okay, defined by such a way such that I of fx will be minus 1 to 1 f s dx. This is the definition of I, and this is it's given as a linear functional. Okay, and we have no need to prove. It is given a linear functional, means it is linear plus functional. Since mapping from a non-linear space to scalar field, so it is functional, and it is linear also. You can easily prove it is linear. Okay, but it is given also, so no need to prove it is linear. Now k is the kernel of this linear. Okay, if it is linear function, then you can easily compute its kernel. You will easily find its kernel, and its kernel is given is k. Okay, so what is the kernel? You can, I'm writing the kernel. What is kernel of this? Kernel of I. What is kernel of I? According to definition of kernel, you can write it: f belongs to those c minus 1 comma 1 such that those continuous function belongs to a set kernel for which I set and those I set 0. Okay, kernel is a set of all those functional. Kernel is a set of those functional which are mapped to identity of the codomain. The identity of codomain will be 0. Okay, So the kernel is suitable those functions which map to 0. Okay. Now if after definition if you can write f belongs to c minus 1 comma 1 close interval. Okay. Now if you can write this minus 1 to 1 if it is the definition of if. Okay. So kernel is suitable those functions for which minus 1 to 1 integral will be 0. Okay. Means kernel contains those elements for which minus 1 to 1 integrate. If you integrate minus 1 to 1 dx, it will give 0. Okay. Definition of I. Now it is given k. In question it is given k. Kernel is k. Okay. It is given k. You can name it 1. Say k is the kernel of the function. Okay. Now there are one more also function given. F is equal to s square in gamma. It is given f is equal to s square in gamma. Then find the distance from k from the function to the subspace k. Okay. Means kernel. So here also one more given. Also given 3 f is equal to s is equal to f is equal to s square. Okay. Where x belongs to obviously close interval minus 1 comma 1. Okay. This is the function given. Okay. Clearly this function, you can say this function belongs to c close interval c minus 1 because it is continuous on the close interval minus 1 comma 1. So it obviously belongs to c minus 1 comma 1. Okay. Now you have to find, what is the question? You have to find the distance between f to k. Okay. So I'm writing that the question. So you understand that what are given c minus 1 comma 1 with supreme norm. Okay, is a normal space. Further is given a functional that send f to minus 1 fs, and the kernel of the functional is given is k. So I am writing that kernel also a function given. Now it is saying that to find the distance from f to this kernel. Okay. So question is find the distance. I'm writing distance between this of f to the subspace k. Distance of f means this f equal to s square. Distance of f to the kernel k. Kernel is subspace. We all know kernel is subspace. Kernel always form a subspace. Okay. When know kernel of a non-space or kernel of a linear space or vector space always form a subspace. So it will be subspace. So distance from the functional to the kernel k you have to find. Okay. So according to definition you can write this. What is the definition of this? You can write the definition. If you write definition, it will be infirm of norm f minus f is minus f minus g of x such that g belongs to k kernel. Okay. So if distance of you can write, if simplify it, then it gives norm of fx minus gs norm of f minus gs where g belongs to k. Okay. The definition. If you can write it more simplified, you can write this like this also. Norm of f is minus gx where g belongs to k. Okay. So you have to find this. This is the distance between f and k. Now here f is given a k x square. Okay. F is given x square. So you have to place in place of f x square. So distance between x square and k is nothing but is the infirm of norm x square minus gx. Okay. Where g belongs to k. You have to find this. Okay. And name it 2. You have to find this. So you have to find this part. So you find the distance, and this is your required question. Okay. So now I find distance. See. So I have to find the right hand part. This part. Okay. So non x comma. So we have to first calculate what is non x comma minus g. You have to calculate. After that you have to take an infirm. So see, in writing one thing that we can always write this 2 into norm f minus g will be equal to minus 1 to 1 norm f minus g dx. Okay. I'm writing this. Okay. So is true. See, norm, I'm verifying that. I'm writing a sentence, and from here in solution will be start. Okay. So I'm verifying that. Suppose we all know norm is a function. Norm is a function here, function from v. Here v is c minus 1 comma minus 1. Okay, with supreme norm, normal space. So supreme norm, you can write it infinity. So norm is a function from polynomial space to scalar field. You can say r plus 0. Okay. So if I take f here, then it gives norm give a real number, either r plus the positive real number or maybe 0. Okay. So if I take g here, so norm g gives same r plus r plus will be a member of r plus union 0. It may be positive real number or union 0. Okay. So similarly, if you take the function and take difference, take them difference. If you take two function f and g from c minus 1 comma minus 1, and if you take the difference, then this function also belongs to c minus 1 comma minus 1, means b. Okay, the difference of two quantum function is also a function. So if you can compute the norm f minus g, this also be going to be r plus 0, member of r plus 0. Okay, it either be a real number or real number or maybe 0. Okay, so if it's 0, suppose if it's 0, then this gives this left hand side will be 0 and this also 0. So this equality hold into side. Okay, but if it's positive, suppose if it's positive, r's, if a real number, a positive real number. If it's positive, then here from here in left hand side, this is that you get 2r, and 2r. From here it is positive real number, so it will be outside. So it will r, integrate it will give 2, so it will be 2r. So each of side are equal. Okay, 2r. So in any case, if it 0, then this equality hold. If it positive real number, then also equality hold. Okay, so it is true. Okay, always. So now using the result, I start my solution. Okay, so I'm writing that part again, and I will start my solution. So I can write 2f minus g equal to minus 1 to 1 norm f minus g. Okay, this is true. So from here you can write easily minus 1 to 1 first bracket f minus g dx. Okay, what I have written, see, we always know for a normal space, for any x belongs to v in a normal space, here c minus 1, normal space will be c minus 1 minus 1. Okay, you supreme norm. So you can always write normal space will be greater than or equal to x. So for any v belongs to, if c minus 1 minus 1, you can always write it norm is always will be greater than f. So similarly, say f minus g belongs to c minus 1 minus 1 close interval. So you can write here for norm f minus g will be always greater or equal to f minus g. So I use this inequality here. Okay, see norm f minus g will be greater than f equal to f minus g. So I have, if you integrate them, so this gives integral under norm f minus g dx will be greater than or equal to integral under f minus g dx. Okay, now what happened? Here f is x square. Okay, now see f is x square, so you have to put f equal to x square, so it gives x square minus, you can write gx. Okay, so this gives not 2, this is the minus integral, this will be greater equal to sign. Okay, but I am putting f equal to x square. In case here in this problem f equal to x square, so you have to put x equal to x square, put x equal to x square. Okay, so this gives greater equal to minus into 1 x square minus g of x. Okay, so this gives if you integrate separate term into g minus 1 to 1 gx dx. Okay, now this integration you can compute easily. Okay, it is nothing but even function. So first of all, it gives 2 times 0 to 1 x square dx. Okay, I am writing this integral minus 1 to 1 gx dx. There is a trick to compute this integral. What is its value? Okay, I will tell you after this. So this gives x cube by 3, this is 1 upon 3. Okay, minus r, it will be left minus 1 to 1 gx dx. Okay, so this gives will be 2 by 3 minus 1 to 1 gx dx. Okay, so from here you can tell 2 x square minus gx norm greater than or equal to, from here you can tell 2 norm x square minus gx. Okay, this will be greater than 2 by 3 minus integral under gx dx. This will hold for x belongs to close interval minus 1 comma 1. Okay, now you will be left with this. Okay, I name it 2. Now see, here g is coming from k. Okay, g among the difference on g is coming from k. And what is k? K with the kernel is given. K with the kernel of the linear function I. Okay, so g is coming from k. The g is coming from, note that now since here g is coming from k. Okay, it's coming from k, and k with the kernel of the linear function I. So from here you can tell then I send g to 0. Okay, it's the linear function, so it may be the identity of the scalar field. So identity of the scalar field R will be 0, so it maps g 0. So this gives -1 to 1 gx dx, this will be 0. So this integral will be 0. Okay, so this is the trick. So from here you can place it, this integral value will be 0. So if you place this integral value will be 0, so this gives 2 into x minus gx greater than 2/3. Okay, so using this you can name it 4. So using 4, 3 becomes, if you use 4, then 3 becomes, what 3 becomes 2 into norm x square minus gx, this will be greater than 2/3. Okay, now if you can take out 2 common from both side, so if you take 2 out from both side, from this gives norm x square minus gx, this will be greater than 1/3. Okay, and this will be true for all x belongs to -1 comma 1. Okay, so if you place again here f x equal to f, so this gives f equal to fx minus gx is norm greater than 1/3 for all x belongs to -1 comma 1. Okay, now this will be greater than 1/3. Okay, now we know in form of this, since f is minus g is greater than 1/3 for x equals c minus 1 1. Okay, you can, from here you can easily tell that in form of this, in form of norm, in form of fx minus gx, okay, will be greater than 1/3 where g belongs to k. Okay, you can tell that since each for f belongs to f minus gx greater than 1/3 for x belongs to 1/3, also it will be true for any g belongs to k. Okay, I have taken g from k arbitrary. Okay, because here f is fixed, I have fixed f equal to x square, but g can vary. Okay, g can vary. I have taken g is arbitrary. You have to take here let g belongs to k be arbitrary. Okay, so g is arbitrary, so g can vary. So from here you can tell that in form of f is minus g is greater than 1/3. So in form of f is minus g is where g belongs to k is nothing from definition, you can tell it is the distance from f to k will be greater than 1/3. Okay, so it is the number 5. So distance between f to k greater than 1/3. Now you have to prove this reverse similarity, means distance of f comma k will be less equal to 1/3. Then you can easily tell distance 1/3. Okay, so for the reverse similarity I am using also trick. So what is the trick? So see, for reverse part. Okay, for reverse inequality, for reverse inequality you have to prove this. You have to prove, what you have to prove? You have to prove distance f of f from k will be less than equal to 1. You have to prove this. Okay, reverse inequality. So our aim is this, to prove this. So I am proceeding. See, I am taking a function. Okay, let I am taking a function g, defining function. Obviously -1 1 close interval, because it whole function are defined on -1 1 close interval. Okay, so defining a function g from -1 1 close interval to r, a real root function defined on -1 1. Okay, by, so I am defining it, you can name it g1. Okay, by, because there is g present. Okay, so g1x will be, I am defining it x square minus 1/3. Okay, where x belongs to -1 1 close interval. Okay, so it is no need to check that this function is a continuous on -1 1 close interval. So you can tell that g belongs to g minus 1 c minus 1 close interval. Okay, with supreme norm. Okay, now if you compute is integrate under -1 to 1 x, compute it now. If you compute it -1 to 1 g1x dx, I am computing this. What is this? -1, this will be x square minus 1/3 dx. Okay, So this is integrate will be separately. If you separate this integrate this x square dx, it gives 1/3 will be outside minus 1 to 1 dx. Okay, so this gives x square is even function, so it gives 2 0 to 1 x square dx. It gives 2/3, so it gives 1/3, so the 2/3, 2/3 minus 2/3, so this gives 0. So what are you seeing is seeing minus integral under minus 1 g1 dx will be 0. means it imply integral under minus 1 to 1 g1 x dx, this gives 0. And this is nothing but a definition of kernel. Okay, if you look out the definition of kernel, what is the kernel definition? See, I have written here definition of kernel. If integrand under minus 1 to 1 fhds will be 0, then that member belongs to kernel. Okay, so since integral under g1 x dx will be 0, so you can say if g1 integral under g1 x will be 0, so you can tell g1 belongs to kernel by. Okay, so you can say this g1, belongs to kernel. Okay, so you can say from here you can say this g1 belongs to kernel of I, or kernel of hk, so g1 belongs to k. Okay, now g1 belongs to k. So now what you can done now g1 belongs to k. Now see, this is the definition. Distance of f minus 2 subspace k equal nothing but the infimum of norm fx minus gx such that g belongs to k. Okay, this is the infimum of this set. Okay, so if it infimum, then it will always less equal, you can write it less equal to a member of the set. Okay, infimum of the set will always less equal to be the infimum of the member in the set, of the set. Okay, because infimum it always less equal to a member of the set. So you can write a member of the set will be this f minus g. If you can vary g. Okay, you say infimum norm of f minus g where g belongs to k, you can vary g. If I vary g, I take g equal to g1, then this is a member of the set. Okay, this will be the member of this set, whole set, infimum of this set. Norm of f minus g, this is the member of this set, so and it is the infimum, so it is always less equal to this norm of f minus g1 x. Okay, now norm of f minus g1 x. Okay, now norm of f minus g1 x, and means if x minus g1 x, this is nothing but what is norm if minus g1 x. You have to compute this. Okay, so I am naming it 5, naming it 6. Okay, you have to compute fx minus g1 x. So x square g1 x, if you compute fx minus g1 x, see if you have to compute norm fx minus g1 x. See, since g1 I am defining g1 x will be x square minus 1/3. Okay, I have defined this. Now x square will be fx itself, so it will be becomes fx minus 1/3. Okay, now from here you can write fx minus g1 x will be equal to 1/3. Okay, so if you take norm from both sides, so fx minus g1 x, this will become 1/3 itself. Okay, so it is 1/3 itself. So if it's norm f minus gs, this will be 1/3 itself, so it will be 1/3. So you get distance of f minus k will be less f comma k, distance of f comma less equal to 1/3. Okay, from here you can write that distance of f comma k will be less equal to 1/3. This is our aim to prove. Okay, so I have to prove. You can name it 7. Okay, so this is our aim, and I have proved that distance of f comma k less than 1/3. Previously I have proved distance of f comma k greater than 1/3. See here, I have proved distance of f comma k in 5. I proved distance of f comma k greater than 1/3. Now I prove distance of f comma k less than 1/3. Okay, from it was 5, distance of f comma k greater than 1/3. This was 5. This was 5. I prove further distance of comma less than 1/3. So together will imply 5 and 7 will be distance f comma k equal to 1/3. So if from 5 and 7 you can say distance of f comma k equal to 1/3. Okay, so distance from the function f, or f is x square, so you can write like this: distance x square comma distance from x square to the subspace k with the kernel of the Euler function will be 1/3. Okay, and 1/3 is the answer for this question. Okay, so hope you understand my solution. Okay, if you have any problem, you can always ask in the comment section. Okay, and any doubt you can always ask in the comment section freely. Okay, so please subscribe my channel and like my channel. I'll upload more video, more lecture regarding this. Okay, of CSIRNET-JRF also. Okay, so see here answer is written on third. Okay, it is official answer. So thanks for watching and please subscribe my channel. Hope you are enjoying my videos. Okay, so thank you.